All right, welcome to our unit on gases. Today's topic is kinetic molecular theory and gas stoichiometry. Lesson 1 of 3, your objectives are as follows. To understand the basic assumptions of the kinetic molecular theory, to understand standard temperature and pressure, or STP, and to understand the molar volume of a gas at STP. So for your quick write, do you think gas particles ever stop moving? What do you think creates the pressure in your bike or car tires? If you heat up gas particles, do you think they move faster or slower? And then a little review here. If you have a mole of oxygen molecules, then how many molecules do you have? And what are the 7 naturally occurring diatomic molecules? Go ahead and pause this while you do your quick write. I'm going to move on. All right, so gas, pressure, and temperature. Pressure is defined as the amount of force for a given area. The more collisions that occur in a canister or a gas container, the higher the pressure in that container. Temperature is defined as the average kinetic energy of the molecules. Therefore, the faster the molecules or atoms move, the higher the temperature in the container. And the faster the molecules move, more collisions can occur, also increasing the pressure. Gas, pressure, and temperature. Consider a bicycle tire. Okay, by pumping more air into the tire, you are creating more collisions, therefore increasing the pressure. Now imagine you take your bike tire out on a hot summer day. By raising the temperature of the bike tire, you are creating more collisions, which also increases the pressure. So, for your notes, what is the relationship between gas, temperature, and pressure? Okay, question on the left-hand side, answer on the right-hand side. Go ahead and pause this while you write. I'm going to move on. All right, so the kinetic molecular theory. The concepts of gas, pressure, and temperature have led scientists to develop a simple model that explains the behavior of gases. This model is the kinetic molecular theory. Okay, the assumptions of the kinetic molecular theory, KMT, are stated below. Gases consist of tiny particles, atoms or molecules. Makes sense to me. Gases are made up of particles with no defined volume, but with a defined mass. In other words, the space they take up, their volume, is minuscule compared to the distances between themselves and other molecules. The particles are in a constant random motion, colliding with each other in the walls of the container. These collisions with the container cause the pressure exerted by the gas. And 4, the particles are assumed not to attract or to repel each other. And 5, the average kinetic energy of the gas particles is directly proportional to the temperature of the gas. In other words, the higher the temperature, the faster the gas molecules or gas particles. Okay, so for your notes, okay, what is the kinetic molecular theory or KMT? Okay, go ahead and pause this while you write. I'm going to move on. Okay, so standard temperature and pressure. When performing gas experiments, scientists often use a standard set of conditions. STP stands for standard temperature and pressure. Chemists use a unit called atmospheres, abbreviated ATM, when measuring the pressure of a gas. To measure the temperature of a gas, chemists use a unit of temperature known as the Kelvin scale, abbreviated K. Okay, so for example, this gas here has a pressure of 1 atmosphere and it's at a temperature of 273 K or Kelvin. So STP is a set of conditions that exist at 1 atmosphere of pressure, okay, and a temperature of 273 Kelvin or K. Okay, so for your notes, what is standard temperature and pressure? Okay, go ahead and pause this while you write, and I'm going to move on. Okay, so gas stoichiometry. At 0 degrees Celsius and 1 atmosphere pressure, all gases behave in a similar fashion. At these conditions, 0 degrees Celsius and 1 atmosphere pressure, okay, by the way, 0 degrees Celsius is also equal to 273 Kelvin, okay, 1 mole of gas atoms or molecules has a volume of 22.4 liters. So at 273 Kelvin, or 0 degrees Celsius, same thing, and 1 atmosphere of pressure, okay, 1 mole of gas atoms, or 6.02 times 10 to the 23rd molecules, has a volume, okay, of 22.4 liters. Okay, this is very handy to use. So we call these conditions, right, as we just learned, standard temperature and pressure. Recall that a mole of gas also has a number of gas atoms or molecules equal to Avogadro's number, 6.02 times 10 to the 23rd. So 1 mole of any gas at STP is equal to 22.4 liters and contains 6.02 times 10 to the 23rd atoms or molecules in it. Okay? So it doesn't matter what type of gas it is. It could be carbon dioxide. Okay? 1 mole of carbon dioxide gas occupies 22.4 liters at STP and contains 6.02 times 10 to the 23rd atoms or molecules. Okay? It could be chlorine gas, same thing. It has a volume of 22.4 liters, okay, at STP and contains 6.02 times 10 to the 23rd atoms or molecules. Okay, and it could be oxygen gas. Once again, the same thing. Any gas at STP, okay, whether it's oxygen, chlorine, carbon dioxide, has a volume of 22.4 liters, okay, and contains 6.02 times 10 to the 23rd atoms or molecules. Okay? So the point is that any gas at STP, in case you haven't figured it out, has a volume of 22.4 liters and contains 6.02 times 10 to the 23rd atoms or molecules. Okay, so for your notes, what is the molar volume of a gas? Okay, question on the left-hand side, answer on the right-hand side. Make sure you write down the conversion factor. Go ahead and pause this while you write. I'm going to move on. Okay, so practice. A sample of nitrogen gas has a volume of 1.75 liters at STP. How many moles of N2 are present? Okay, so go ahead and pause this while you do this. Okay, check your work here when you're ready and hit play. All right, let's see how you did. So start with what we know. Okay, let's think of our conversion factors. We know 1 mole of N2 gas at STP has that volume, right? We just wrote that down in our notes. Okay, so liters of nitrogen gas cancel, and we get 0.0781 moles of N2, or 7.8 times 10 to the negative 2. Okay, hopefully you got that right. Getting a little more difficult now. Okay, so practice. Okay, quicklime, calcium oxide, is produced by heating calcium carbonate, okay, CaCO3. Okay, calculate the volume of CO2 produced at STP. Okay, remember carbon dioxide is a gas produced at STP from the decomposition of 152 grams of calcium carbonate, according to this reaction here below. Okay, I kind of got it going here for you already. So go ahead and pause this while you do this. Okay, when you're ready to check your work, hit play. Okay, let's see how you did here. Okay, start with what we're given here. 152 grams of calcium carbonate can produce how much? Okay, what volume here of carbon dioxide gas? Okay, so we know 1 mole of calcium carbonate has a molar mass of 100 grams of calcium carbonate. Okay, and we know 1 mole of CO2 can be produced by 1 mole of calcium carbonate. It's our molar ratio. Okay. And finally, we know 22.4 liters of CO2 at STP, okay, is equal to 1 mole of CO2, right? I have moles here. I'm going to need moles of CO2 there. Okay, our units cancel. And we get 34.1 liters of CO2 can be produced. Okay, hopefully you got that right. Go ahead and summarize. Go ahead and pause this while you do your summary. Remember, you can always do your own, and we'll see you next time.